Hello everyone, my name is Hamza Baniata. I'm gonna be instructing and lecturing today about the tool, namely FoBSim, which is an abbreviation for Fog Blockchain Simulation. Um, and just briefing about your instructor, I do research and lecture about blockchain integration with different trending technologies, including uh, for computing, cloud computing. I always take into consideration the privacy and the GDPR compliance in the proposed tools and protocols. I research the optimization of blockchain in different contexts, and of course, I always take care of the security of the system. And I have recently um, um, started working on the integration of blockchain and AI, how to enhance blockchain using AI, and of course, how to utilize blockchain in the AI context. And in this series, I'm going to be only lecturing about the FoBSim tool, but we do have other lectures about other tools that we proposed. And basically, I work as a research fellow in the IoT Cloud Research Group at the University of Saget. Just a short thanks to the European Cooperation in Science and Technology program. They have generously funded this tutorial. COAST is a funding agency for research and innovation networks, and it helps connect research initiatives across Europe. You can check out their website, and you can participate in any action that align or is in line with your research directions. In this tutorial, uh, I will provide a series of short videos. Each will cover one of the headlines presented in this slide. I will give a brief introduction to blockchain for computing and their integration architectures and services. And following, I will cover some aspects of the simulation tool presented in this tutorial, and I will provide hands-on example on how to download and utilize the open source version of the tool. And finally, I will present some of the performance evaluation of systems simulated using FoBSim and conclude the tutorial. So fog computing is basically the extension of the cloud computing at the edge of the network. Service models usually provided by the clouds include infrastructure as a service, platform as a service, and software as a service. And those service models basically target the storage, computation, and communication services provided to end users in a flexible and dynamic way. The fog is conceptually a distributed micro cloud platform closer to the end user layer to provide the same cloud services with lower latency and higher security. Now, different fog integration architectures were proposed in the literature. However, all of these architectures agree on these criteria. Whenever we integrate blockchain with a cloud or fog-enabled solution, we can state that the cloud is providing blockchain as a service model, where blockchain computations and applications can be deployed in the cloud or in the fog. Typically, the framework of a fog-enabled system is defined as in this figure. So here, end users send storage or computational tasks to the cloud through the associated fog nodes. If processing those tasks comply with the service level agreement between end users and cloud service providers, the fog platform performs these tasks swiftly and returns the results to end users. Later on, fog nodes can exchange configuration and update data with the cloud, which is the main fog service provider, which is the simplified, let's say, view of how services are provided in a fog-enabled system. This is not concerned with the blockchain or any other complex contexts. This is just generally how we can rely on the fog in order to provide cloud services faster than the cloud. Blockchain-based solutions are usually described referring to five main layers, including infrastructure, data, network, consensus, and application. The first three layers are usually constructed and maintained by non-blockchain practitioners, yet they need to provide protocols and mechanisms that are suitable for the application layer. For example, we need a peer-to-peer network in the network layer, and we need to define the proper cryptography methods in the data layer. We might need a trusted third party for a permissioned application or a trusted execution environment for proof of elapsed time consensus model, for example. The ledger can be defined referring to the required security level of the system or the specifically consistency level required by the system. It can be linear or DAG, etc., etc. Until the year 2009, we only had one model to guarantee the security of distributed systems, which is the BFT model, or the Byzantine fault tolerance model. This approach tolerates at most a third of the network nodes to be malicious or faulty. However, blockchain technology introduced by Satoshi Nakamoto in 2009 proposed higher tolerance for up to 50% of the nodes. This mechanism consumes, however, a lot of energy and has low throughput compared to centralized solutions, which triggered the research community to propose several alternatives, such as the proof of stake, the proof of authority, and proof of elapsed time, etc. There are at least 40 alternative consensus algorithms that I know of, but it depends on also the application and the throughput required, and the security level, of course, that you need, which defines which consensus algorithm needs to be employed. The BFT specifically is very costly in terms of message exchanges. So we have a very high network load in the BFT model. In the proof of work model, we have moderate level of network load, but at the same time we have high energy consumption or high computational cost. The application layer consists of the definitions and aims of the system, and accordingly different layers can be set to fulfill the application requirements in general in order to provide the needed service at the end of the design or the implementation. Now, several advantages of integrating blockchain with other technologies we can find them, including reduced congestion due to the distributed nature of the network and higher trust and reliability levels of the system, since there's no controlling trusted third party. The immutability criterion is sometimes described as disadvantage. We will talk about this in a bit. This is typically how the blockchain system is formed. We have different nodes and they are connected in a peer-to-peer fashion. They are connected usually randomly to each other, and each node maintains its own local chain of blocks, as you can see at the bottom. And each block has some attributes. It has headers. It has transactions within, and each block is connected to the previous block logically and using let's say linked list. But at the same time, it's logically connected using the previous data in the previous block. It's kind of embedded into next blocks so that any alteration of any previously confirmed block would require the modification of all uh, preceding um, blocks. This is a simplified view of the ledger where blocks are appended to this ledger such that each block is connected to a previously confirmed block. Once the block is confirmed, the next block should also point to it. The cryptography utilized behind the scenes, including robust hash functions and asymmetric encryption, is reliable enough to, let's say, claim that it is inefficient to crack this cryptography systems or schemes. Each block consists of several types of data and attributes, as we said, and this data defines the block and assures that it is accessible. Examples of these attributes include the proof of validity, which might actually differ according to the consensus algorithm deployed. In POW, or proof of work, for instance, the proof is a hash of the body of the block, let's say the body in the block that necessarily has a predefined number of leading zeros. In proof of authority, the proof is simply a signature of the authorized miner that can be verified with low complexity, yet cannot be forged. Several technical details can be deduced about the whole system from a single block, such as the type and version of the algorithms utilized, full list of transactions confirmed within this block, including the accounts that triggered these transactions or received these transactions and funds, etc. So once a block is added to the chain, it cannot be changed and modifications must be performed in following blocks. The components of blockchain are many, but we can list or discuss the major components. We have the distributed ledger, as we said, and this is saved locally in all network nodes. So we have as many replicas of this ledger as the number of nodes. Any change to this ledger should be agreed on by a majority of the nodes, and data added to the chain cannot be deleted whatsoever. Each block has predefined number of transactions or has predefined value of transactions held with them. The consensus algorithm, which is also called the validation protocol, is a process set to reach agreement on a single data block among multiple unreliable nodes, which are the nodes of the blockchain network, which do not trust each other. Examples are already mentioned, but we can also add the practical Byzantine fault tolerance, the PBFT, and this is mistakenly written here. So it's practical Byzantine fault tolerant. And we do have the delegated BFT, and we have the delegated proof of stake and stuff like that. Third, we have the smart contracts. This is not really or necessarily present in all blockchain systems, but we can actually map everything to be a smart contract. Even in Bitcoin, we do know that there's no smart contracts available, or smart contract functionality in Bitcoin, but still you can think of the code run once you submit your transaction as a smart contract, but it seems like in Bitcoin we only have one smart contract performing only one task, which is utilizing the UTXO model to perform monetary transactions. The smart contracts are managed by the network protocol using same idea of traditional contract, but with the signature being anonymous and private using the asymmetric encryption.